Every single time you send an email, buy something online, or even just log into an account, you're trusting a secret keeper. But here's the thing. This keeper isn't a person or some super complex computer chip. It's just math. And in this explainer, we're going to pull back the curtain on the elegant and pretty ancient mathematics that form the bedrock of our entire digital security. So, let's start off with a little puzzle. Take a look at these two numbers, 259 and 621. What do they have in common? At first glance, they seem totally random, right? But they share this hidden connection, and finding it, well, that's our first step to understanding how modern cryptography really works. We're going on a bit of a three-part journey today. First, we'll solve that puzzle by finding something called the greatest common divisor. Then, we're going to dive into the really mind-bending world of modular arithmetic. You can think of it as clock math. And finally, we'll see how mathematicians build absolute, rock-solid certainty with the incredible power of proof. Okay, so to crack our puzzle, we need a tool that's, get this, over 2,000 years old. It was invented by the Greek mathematician Euclid. And it's an algorithm, basically just a set of rules, for finding the biggest number that divides into two other numbers without leaving any remainder. And this right here is the Euclidean algorithm in action. It looks a little intimidating, but the process is surprisingly elegant. We start by dividing the larger number by the smaller one to find the remainder. So in step 1, that remainder is 103. Now watch this. This is the clever part. That remainder, 103, becomes our new divisor in step 2. We just keep repeating this process. The remainder from one step becomes the key to the next, over and over, until we just can't go any further. And there it is. The final answer, our last non-zero remainder, is just 1. That's the hidden connection we were looking for. It means these two numbers are co-prime. And that simple little property, believe it or not, is a cornerstone of modern cryptography. It's absolutely essential for creating the public and private key pairs that protect all your data. Of course, there is another way to do this. You could try to break each number down into its prime building blocks, its fundamental DNA, and then see what they share. But just imagine trying to do that for numbers that are hundreds of digits long. No way. The Euclidean algorithm is just so elegantly efficient, which is exactly what you need for today's high-speed security. All right, now let's build on that with something even more powerful. We're about to leave the world of boring infinite number lines and start thinking in circles. Welcome to modular arithmetic. This, my friends, is where the real magic of cryptographic math begins. Modular arithmetic sounds really complicated, but it's simpler than you think. Honestly, just think of a clock. If it's 10 o'clock and you add 4 hours, you don't say it's 14 o'clock, right? You say it's 2 o'clock. The numbers just wrap around after 12. That's all modular arithmetic is. It's the math of what's left over after you've wrapped around a certain number, which we call the modulus. Okay, so keeping that clock idea in mind, take a look at this monster of a problem, taken right from a cryptography course. Your calculator would just give up trying to compute this. But with modular arithmetic, we can actually tame these impossibly huge numbers. So the first step is to shrink that big number, 2020. In the world of Mod 11, all we care about is the remainder when we divide by 11. Turns out that's 7. So for our purposes, the huge number 2020 behaves exactly like the tiny number 7. We can literally just swap it out. And here is the really brilliant part. In Mod 11, the powers of 3 actually repeat in a predictable cycle. And because of that cycle, that massive exponent of 2020 is no longer a problem. All we care about is its remainder when we divide by the cycle's length. This simplifies that exponent all the way down to 0. And anything to the power of 0 is just 1. Amazing. So just like that, our monster problem has been whittled down to this, a much simpler calculation. By thinking in circles, we traded a totally impossible task for something we can actually solve in seconds. And the final answer? It's 0. That means that enormous, terrifying number we started with is perfectly divisible by 11. And this ability, the ability to make massive calculations predictable and manageable, is exactly what makes modern encryption possible on your computer or your phone. But all of this leads to a really critical question. We've seen these tools work for a couple of examples, but how do we know they work for every number, every single time? For that, we need our final concept, the unbreakable power of proof. You see, when we're talking about protecting financial transactions or state secrets or just your private messages, it seems to work is not an acceptable answer. Not even close. We need a guarantee. And a mathematical proof is that guarantee. It's a logical argument that leaves absolutely no room for doubt. One of the most powerful ways to build this certainty is a technique called proof by induction. The best way to picture it is like a line of dominoes. First, the base case. You have to prove you can knock over the very first domino. Simple enough. Then, the hypothesis. You just assume that any given domino in the line falls. And that leads to the inductive step, which is the real key. You prove that if any domino falls, it will definitely knock over the one right after it. This is that final, logical leap. As the source material puts it so perfectly, those two facts together, the first domino falling and the guarantee that each domino knocks over the next, prove the entire claim. It creates a chain reaction of certainty that can stretch on to infinity. And this is the foundation of trust in our systems. It isn't magic, it's just an unbreakable chain of pure reasoning. This is what allows us to be certain that the math protecting our data is going to hold up, not just for the numbers we've tested, but for any number, no matter how big it gets. So there you have it. Ancient algorithms, clock math, and proofs that work like falling dominoes. These incredibly elegant, simple rules are the invisible guardians of our entire digital world. But it leaves us with one critical question. In a field that is built on absolute certainty, what happens when a new discovery suddenly breaks the old rules?